Hello everybody, my name is Torsten Hoefler. I'm a professor at ETH Zuerich and I'm glad to present the Machine Learning Day at ISC 21 to you. So this is really a summary of large-scale machine learning and high-performance computing, what happened in 2020 and the first part of 2021, what is most likely going to happen in the remainder of 21 and in the near future, or at least my predictions thereof and also the predictions of the participants or speakers of the Machine Learning Day. So machine learning in 2019, 2020, I gave an update at last year's ISC in a very similar form. And there were very interesting academic and industry developments. So specifically, Microsoft pledged $1 billion to OpenAI to pursue the holy grail of artificial intelligence. So artificial general intelligence, machines that behave like computers. You can talk to them, they will talk back, but of course much more intelligent than what we have today with Google Home or Microsoft's Cortana. And for this, they built a very large-scale supercomputer, and this was publicly announced, 10,000 GPUs and 400 gigabit per second network. If you do the math, assuming that these are A100 or NVIDIA's A100 GPUs, which have about 312 teraflop FP16 per piece, this would be a 3 exaflop per second computer. So just a couple of days ago, of course, we have to have a larger announcement, and that was announced by Jensen Huang at the NVIDIA GTC keynote, and this was talking about a Swiss supercomputer. The next generation machine that's following up Pitt Stein, which has traditionally been for the longest time the fastest supercomputer in Europe, will be replaced by a supercomputer, the world's fastest supercomputer for artificial intelligence. 20 AI exaflops, whatever that means, probably something reduced precision floating point, which is perfectly applicable to artificial intelligence, and soon, of course, scientific computing, as far as we understand how to use these kinds of flops and these kinds of capabilities in the context of scientific computing. So furthermore, what we are seeing is more and more specialization in these machines. As you see, they already specialize the data type, moving away a little bit from the traditional FP64, the announcements, they don't even include it anymore, to AI flops, which is smaller data types, less information in it, but more of those at the same memory. So this is a very interesting development, and eventually, of course, we will be hopefully seeing artificial general intelligence, brain-like computers, like these things that we have operating at 20 watts in our minds, and that are actually extremely efficient and for what they do, really, really, really advanced. So we are getting closer and closer. Of course, we are still extremely far away. But now, what are the applications we are running on those machines? Well, the applications are not so much different from last year, but got much more exciting, or at least the technology behind it. But let me just elaborate on this a little bit. Last year I talked about OpenAI's GPT-3, a very large model, extremely impressive, 175 billion parameters, $12 million to train the model. Allegedly, later there were some updates. It was about $6 million, but the number of parameters is not negotiable, which is actually about multiple terabytes of memory to just load the model into main memory. So running inference on this model is also extremely challenging, and this is something I will be talking about in a couple of minutes, because this will be the new challenges, how we actually use these extremely large-scale models that we can train. But this model is highly impressive, like few-shot learners. You've probably seen it in the news. Very interesting results. So you ask interesting questions to the model, you get very, let's call it sometimes unconventional answers that are very surprising in terms of seemingly human-like answers. Because of course, it's a statistical language model of what humans have said, so it behaves very much like a human, but it's really, really astonishing also to me how it performs and what it does. I had a blog post last year that you could look up about a little bit more analysis about the cost, but what happened now this year? So the big news this year that you have probably seen is really the CASP 2020 results. So the biannual competition about predicting protein folding or protein structures, as you can see here, this green and blue. Green is the experimental result, blue is the computer simulation using AlphaFold 2, an artificial neural network like a structure. It has a little bit more than just the ANN, but it was really beating everybody in this competition, which for the longest time has been extremely hard to get good results. And if we, speaking about results, we can see it here. So that up here is the AlphaFold result, 240 something in the score. The next result is really down here, less than half. So really, one can say that they cracked it. They cracked it completely. And the next best is far, far away, and we really see how these artificial intelligence, very large-scale learning techniques benefit science that will lead to new drug discoveries, as you can see here directly. And all of this bases on these transformer networks, very similar to OpenAI's model, very similar to language models. These are sequence-to-sequence transduction models, of course, protein sequences, right? Language sequences, many things are sequential and have complex structures. So one of the major changes in this from AlphaFold 1 to AlphaFold 2 was really replacing the CNN with a transformer model like BERT. But now the question is, how do we solve, or how do we train these very large-scale transformer models? Well, going back to the comment up here, HPC, high-performance computing. This is what we do. Very, very large-scale models. Here we are seeing a transformer model as a block diagram, so it's a relatively simple structure. It's still computationally quite hard to understand what it's doing, where the data is flowing. But there are three aspects to this to make this work at this large scale that is required to run it. So one is in the embedding layer, which is at the very beginning of the network, where you have to read all your data and you have to deal with the quickly growing data volumes in scientific computing. So specifically, what we can do there is we can exploit the features of machine learning workloads that have very particular ways of reading data. So for example, they're reading data in a random order, but the order is not truly random because it's a pseudo-random order. So there's some kind of pseudo-random number generator which you can predict. And well, if you can predict your I/O access pattern, you can do intelligent prefetching. And actually, if you do this across a number of machines, you have reuse across these machines, and then you can intelligently design an I/O schedule to exploit the features better. So there's a paper on this clairvoyant prefetching that you could look up what this really means in details. I don't have enough time to talk about all these developments here. So second, once you have loaded the data, you need to process it as efficiently as possible in a deep learning setting, of course, mostly on GPUs today. And there, deep learning is really like high performance computing. It is crunching a lot of numbers, smaller precision numbers, but at the end, it's very much like linear algebra. The same major problems that we've talked about for years now. Data movement is the major problem, and there's a paper on data movement is all you need, really describing on how to make these transformers faster. The main conclusion there is that really, yes, even machine learning algorithms are in the data movement limited regime because computational units got faster and faster as we reduced the data type size. Of course, we got more performance, but the relative ratio of compute to performance was tilted very much, of compute to data movement, was tilted very much unfavorably towards the data movement, so which became much, much, much more important in the near in the recent past. And then the last piece is high performance communication systems. So we're using larger and larger clusters to train with tens of thousands of GPUs. We have data parallelism is not sufficient anymore. We have to go to model parallelism. We have to go to complex pipeline schemes, operator parallelism, and sparsification. So there are several papers. One of them is our survey that really summarizes how parallel and distributed deep learning at large scale could be conducted. And all the schemes summarizing about 200 papers in this field that show the state of the art of large-scale deep learning. So, and much of this is actually used towards the BERT-style models into the near future. So, but now I've also mentioned that there is an IoT edge story in high-performance computing. So as we are moving from centralized data center computing to more of a distributed computing where every device has some kind of intelligence in it. I have a smartwatch. Actually, when I'm walking through my village, every single street lamp here in Switzerland has, or at least in my village, has a smart sensor built in that predicts when a human is walking by and actually lights up the path for you before you even walk by. So there's a form of communication between these lamps, and you walk down the road and you can see the lamps lighting up in front of you, kind of a very royal feeling when you're walking at night. So quite nice technology. And all of this is, of course, small devices at the edge that will be connected or are already connected using 4G, 5G technologies. But all of these devices are extremely small. So these large models that I mentioned before, 3.5 terabytes, are not going to fit into those devices. So we need tiny scale models. How do we get to these tiny scale models from the super large models? Well, we have to somehow compress and sparsify our models. And I want to specifically emphasize the sparsification aspects of it because in my view this is one of the most exciting topics where we could employ high performance computing in the very near future. But the intuition about sparsification is that not all features of the model are always relevant. So what does that mean? Well, you can test your brain while I'm speaking at this sentence. You can read it here. The sentence does not give you all the features, it's not fully correct, but I'm sure you can guess what it means and you get the essence of the sentence. Because if we sparsify inputs and layers, we are still working in the same large vector space, just with less data, which leads to less overfitting, higher interpretability because we have less things to worry about, and of course parsimony in the sense that we have a much smaller model that we can run on smaller devices. And the key ideas here is we really remove neurons of the model and all associated weights, or we remove single weights, so single connections between specific neurons in the model. There is a lot to be said about this. I don't have enough time in this very coarse summary, but the key results are that for image recognition networks or detection, so image processing networks like ResNet, we can reduce the parameter count by 20x, and the compute, of course, as well, by 20x with essentially the same prediction quality, essentially the same output quality. So this is something I find extremely exciting. Furthermore, there are many, many research opportunities because what you usually do is you invest a lot of compute into making this happen, into sparsifying models. There is that they run on the edge on IoT device. And what's even more exciting is we can train sparsely. So we can train in very large vector spaces with sparse representations, which technically increases the knowledge or the knowledge representability, so the information content of the deep neural network. So there's a survey that I and some colleagues have written on this topic, and this is something that I believe will actually grow bigger and bigger and bigger in this particular context in the near future. So now the ML Day at ISC is squarely addressing all these topics in 2021. So we are starting with a session organized by Peter Dubin on machine learning and climate and weather from an ECMWF perspective, covering many aspects because there's a large number of observations on the Earth system. We can now learn from these numbers, from these petabytes of data that they have on disk, and also many simulation results and many advanced sensor inputs that you could learn from, organized in observations, data assimilation, numerical weather forecasting, and post-processing. So these are all features that could be used or could be enhanced by machine learning. Specifically, I find post-processing quite interesting because I and my group have contributed a bit in this area to increase the accuracy of post-processing pipelines. So a second topic, a second session organized by Rio Yokota is going to discuss scalable optimization methods for deep learning. Specifically, we have a speaker from NVIDIA, stochastic layer-wise normalized gradient descent. We have a speaker from Japan who now recently actually joined my group in Zuerich, Kazuki Ozawa, talking about second-order optimization or beyond first order. And we have a speaker, Yang Yu, used to be a PhD student at Berkeley and is now an assistant professor of fast and accurate deep learning. The third session will be machine learning tools and for systems, organized by Mariam and Tal. And this will be opened by Amir Golami, talking about integrated approach or a way to design deep neural networks. Then we have a talk by Tse Zhang from ETH Zurich, who's going to talk about large-scale distributed learning and tools, specifically lossy and unreliable channels, which is quite an interesting topic. Furthermore, the last session will be organized by Craig Stewart, who secured two very interesting speakers, Julie Clem, program director at the NCI Institute and Initiative, who's been working on COVID-19, and Manish Parashar, many of us know him, who's at the Scientific Computing Institute in Utah. With that, I would hope to see you all at the ISC session, at the Machine Learning Day session in video, and I even hope more to see you next year at the real ISC back in the real world once we have won over the pandemic. Thank you very much and see you later.